Good morning, everybody, and welcome. It is New Year's Eve day, 2024, going into 2025. Today's topic is going to be solving the linear homogeneous second order differential equations. This is very important as we move from the dawn of quantum mechanics over into actually doing quantum mechanics. So this is going to be a very mathy day today. Maybe math is not your strong point, or you cringe at the idea of that, or maybe you're really great at math. No matter where you stand, it's very important that we understand how to solve these kinds of equations, because this is going to come up over and over again as we are working our way through the various models in quantum mechanics. So just to give you a bit of understanding of why we're going to need to suffer through all of this, let's just understand what's going to happen. So you probably got the idea already that there's going to be something called the Schrodinger equation, which is going to be coming up really soon. We'll even mention that today, which kind of H psi equals E psi, and why not just divide out by the size on both sides and we're done with that? Well, that's not exactly how differential equations work. Differential equations are going to be a little bit different. They're, in fact, saying something about how the rate of change is going to be for functions. And so oftentimes when we're solving regular algebra problems, our variable is going to just be an x. But in this case, our variable is in fact going to be a whole function y of x, and maybe even y of x and t. And so what we're going to need to do is we're going to need to try to figure out what that function is. So what the wave equation will tell us is it will tell us how we expect it to behave, like what's the generalized behavior. So some of the different models we're going to see throughout the course are going to be solving the classical wave equation, because this gives us a really good foundation for how all of these things work. You may have solved this in a physics class before, but if not, don't worry, we're going to show you how to do it, but that will be for the next time. And then we will start to solve some other kinds of equations where we're going to work on a particle in a box, and also some other models. So the one-dimensional harmonic oscillator, 2D and 3D harmonic oscillator, the rigid rotator, looking at the hydrogen atom are some of the things that we would want to be able to solve. And so we're going to have the basic wave equation. And the basic wave equation takes a form that's a differential equation that's more or less the same for all of them. And it really is the details that we substitute into that equation that are in fact going to make each of these models work in a different way. But what that means for us, though, is that we're going to need to get the form of, like, how do you tackle solving this kind of a problem? And that's really the heart of what we are going to be dealing with today. So what we need to realize is that the wave equation is going to be a differential equation. That is, it's going to look a lot like calculus stuff with some derivatives and so on in it. It's going to tell us about how our system behaves. And what it's doing is it's saying, I'm thinking of a solution, which is a function. So instead of a variable, it will be a function. I'm thinking of a solution that's a function that fits these properties. And as we'll see, the homogeneous property is that all of these things can be set equal to 0. So you have some equation equals 0. And that's what makes this homogeneous. So we're saying, I'm thinking of some function that has this combination of adding together different derivatives that's going to add up to 0. What function am I? That's what we're trying to get at here. And so as we step through this problem, we'll see how we might actually get that function. And the great news is that the mathematicians are really quite a big help for us here, because they've, of course, already thought up the answers to these things. You know, some smart people working on that, and they already told us all the functional forms. So we can just go and look it up, just like in calculus, you might have a lookup table for some of those more complicated derivatives. We will have some lookup tables that will be quite helpful to us when we are going to be solving these things. So we'll be saying, I'm thinking of a function that has thus and such properties of this sum of its various derivatives. Guess which function I am? And that is what we are going to need to be doing today. So with that introduction, hopefully that gives you some idea of what the importance of today's suffering is going to be about, but also will hopefully provide you with some insight on how to actually solve these things. So let me go ahead and just like we did in the previous ones, I'm going to go ahead and share my screen with you and take some notes. I'm going to just turn my camera off here, and they're gonna share the screen share, and I have a notebook set up for you. Okay, great. So here we are. Oops, no, that's the wrong one. Hopefully we can make this one full screen, except the Zoom stuff is on top of this one. How can we make this one full screen? There we go. All right, we're in business. Just as I'm flipping my notebook pages here, I also want to point out that there's a handout available for you that accompanies this lecture. If you don't have it, or maybe joining us from the World Wide Web and you're not actually in the class, no problem. I'll be outlining all of the information as we go through this today. But if you are in the class and you want to have that, some of those information pieces laid out for you, we do have that available for you. So just keep that in mind as you are taking a look at today's class. Now, let's talk about the equations. All right, so it's called let's just unpack what this actually is. So we have the second order. Let's see. Oh, no, we have to be in the right. Okay, second order. What does that mean? This means the leading coefficient of this means the leading term will have a power of 2. In other words, it's going to have something to do with quadratic equation, ax squared plus bx plus c. Do you remember this for the parabola? Parabolas are going to come up. All right. The next aspect of this is that they are linear. What does this mean? This means that the dependent variable, and I'm going to put variable in quotes because it's actually a function. And its derivatives are in a linear form. That means you can't have powers, you can't have squares, no crazy trigonometric stuff in there. It's gonna be linear. So that's great news because they're easy to solve. And then we also have the property that they are homogeneous. And this just means you can write it adding up to 0, right? You can set the equation equal to 0. And there we have now our description of the kinds of equation that we're going to have. So in other words, the kind of equation that we're able to solve with this is in fact somewhat limited, which is great news for us as students of the subject because it means we have solvable problems. But what it also implicates is that there could be much more complicated things. And in fact, real atoms are quite complicated, and this will provide some insight into why we would not be able to actually solve it. So let's get into how to solve these things. How to solve second order linear homogeneous differences. All right, what makes it a differential equation? The differential equation part comes from the fact that it's going to have calculus looking stuff in it, right? It's going to have some derivatives in it. All right, so this is our general form. All right. It's going to look something like this. D squared y over dx squared plus p dy dx plus qy equals 0. All right, let's just check it out and see if this maps up to being a second order linear homogeneous differential equation. All right, so what is our highest term derivative? It's this one right here, d squared, right? Is higher derivative than just plain d, because this, of course, is first order, and this one doesn't have a derivative at all. So this is our second order. So it meets the criterion of being second order. Is it linear? Well, we'll know that when we solve for y. But so far, there's no problems here. Homogeneous. So we recognize homogeneity because this thing is set equal to 0. Equals 0 right here. Terrific. And is it a differential equation? It sure is, because we have calculus things in here. We have some derivatives. Here's a second, first, and no derivative in the various terms. So this is the form that we will be working with. The P and the Q are going to be our constants. Now, just in case you have forgotten about these notations, let me just do a quick refresher for you. So what this is saying is we have some function y of x, and the function is going to, and this is the derivative of that function. In fact, this is the second derivative, right? So you take the derivative, which of course is the rate of change. So this would be the rate of change twice. This is the rate of change once. In other words, the rate of change twice. You might have learned from physics is acceleration. This is just going to be the rate of change. So that's a velocity, and then this is the equation times a constant itself. So this is what it's describing. Now, velocity and acceleration don't exactly translate into our description for the quantum mechanics, but it's going to have to do with the rate of change that's quite analogous to that. So remember that this is going to be describing something about that wave equation for us, right? This is the generalized form. So this is what we have. Now let's just make a few notes. So we have, this is the Leibniz notation. Ooh, and that is a really big font size. All right, Leibniz. So there were two people who discovered the calculus, or who invented the calculus. This is the Leibniz form of it, and the other person who formed the calculus was was Newton, Isaac Newton. They did this independently. Newton was first, but published last, and Leibniz discovered it later, but published first. So they more or less invented the calculus. And this is why we have these two forms of notation. Plus Q equals 0. So you hopefully have some familiarity with both of these. Now these are primes. This was Newton's notation. You would use the double, so you would use each prime means a derivative, right? So this is a single prime for our first derivative, and this is double prime for the second derivative. Now the problem with Newton's notation, of course, is it doesn't say with respect to which variable. So if you only have one variable, it's pretty useful, but if you have multiple variables like multivariable calculus, it's a little bit less clear what exactly it is. And so Leibniz's notation is typically the one that's used in math classes more often, because it explains all of these things very explicitly. So recall that this says, this is the function y with regard to the variable x. And this will come up again when we're doing thermodynamics, which is multivariable calculus. Okay, so we have this one. And as a historical note, the squared actually means the second derivative, but it goes d squared y and then dx squared. Like the square moves places. It doesn't actually mean anything. It's really more of a historical note, but both of these equations in fact mean the same thing. And so what we want to note here is that P and Q are constants and Y is the function variable we are trying to guess. As we solve it. That's the point of doing this. All right, so that's our setup. So now let's get into actually solving this thing. Okay, how to solve. So we're going to go through this in a generic way, and then the rest of today's lecture will consist of, in fact, actually solving this with specific examples. So you'll see kind of like how to apply all of these things. So right now, let's go through and let's talk about how you would do this. All right. So step one, you're going to deduce P and Q by coefficients by inspection. Because we will need P and Q for our next step. So what this means is that if your equation is not in this form, like let's say one of the terms is on the other side, it's like algebra, you're going to move it over to the other side. Suppose you have a number out in front, your leading coefficient is not 1. You're going to divide through by that constant to make it so your leading coefficient is 1. So this means you need to check it before you go ahead and solve. So you need to rearrange if necessary. And you also want to set it up in this order. So you have your highest to your lowest terms. And just like in algebra, you could have the situation that a term has a coefficient of 0 and therefore is missing. I would just go right ahead and write it out explicitly with the 0 next to it, especially as you're getting sorted. So we need to rearrange if necessary, so that your leading coefficient needs to be 1, and they need to be in order. In order and to equal 0, right? So you just move it to the other side of the equation. All right, the other thing we need to do here is we need to divide by the leading coefficient. If it is not 1, to make it 1. Make it be 1. All right. So then we have our equation set up and we're good to go. Step 2. Substitute into the auxiliary equation. This is why I said it's useful to tap the shoulders of our math friends. What does auxiliary mean? It means like supplementary. So it's sort of like this supplementary equation to help us solve this problem. The auxiliary equation is given by this: m squared plus pm plus q equals 0. Oh, looks kind of like a quadratic. This is the auxiliary equation. All right. notice it looks similar to ax squared plus bx plus c equals 0, right? So this is from your algebra class, right, where a equals 1. Right, so that should look familiar. Well, how do you solve this one? This is the quadratic formula. Right. So how do you do it? Well, you can either solve by factoring. Remember, completing the square and factorization and all of these exciting things, or use the quadratic equation. The school math is coming back to haunt us. So remember, we have ax squared plus bx, ax squared plus bx plus c equals 0. And we have, then in this case, we're solving for x equals, remember this one? Negative b plus or minus square root of b squared minus 4ac all over 2a, and this is the generic form. But of course, we said that we made our leading coefficient be 1, so our a is always going to be 1. And in this case, the one we're solving for in our auxiliary equation has this m squared. So instead of solving for x, in our case, we're instead going to have something very much related, but a little bit different. M equals, right, negative p, right? So where this one is matching to our equation. Now look at, that's the b, right? Negative, instead of negative b, it's going to be negative p plus or minus the square root of b squared, which is now p squared, minus 4 times a. Remember that we said a is always equal to 1 because you multiplied out. So it will be 1 times c. Where's the c? That's just q all over 2a. But remember that our a is 1 over 2 times 1, right? So in other words, we have negative p plus or minus square root p squared minus 4q all over 2. This is the one we're going to be using, right? Because of those situations we have. So that matches our auxiliary equation. So we will be substituting into that. Now remember about the discriminant, right? So sometimes when you have the quadratic equation, you're going to have two real roots. You could have a double root, or you could have imaginary roots. Do we remember this? All right, and also the parabola could face up or down. So when we are solving the quadratic equation, what we are thinking about is we're thinking about where does this actually cross the y-axis. And so we have a similar kind of a thing going on here where we're trying to solve this equation, and we also could have different kinds of solutions to this, which could involve real or imaginary answers. And the curious thing that you might remember is that about I, the imaginary number, is that that's how you, I is for the square root of -1, right? So no two numbers multiplied together will make a -1 because you multiply two negatives and you'll get a positive, right? So how do you multiply two things together to get -1 or negative any number? Well, you can't do it, but that's where the imaginaries come in. And so we have also the imaginaries will come in here, but the density function, which is going to be related to the y function, which will tell us where the electron goes, is the square. And so the curious thing then is that the imaginaries actually become really important because you can take the imaginary part, and by squaring it, you can pop it over back into the real, and you can actually get some density sometimes. So it's really quite interesting how all of these algebra things come together in this case, especially if you go on and study quantum mechanics, maybe more like quantum physics. you will see all of these things coming up. Okay, so step 3 is we need to figure out which case of roots we have, and then we'd use the appropriate solution for that. So again, we'll have some nice forms from our mathematical friends who have already solved these problems. Step 3, figure out which case of roots and use the appropriate solution form for that. All right, so let's take a look. So the most straightforward one is case 1. You have two distinct real roots, which means under the discriminant, you're going to have a positive number. So like we have the square root of 4, great, we're going to get 2 real roots, plus and minus 2, something like that. So case 1. You have 2 distinct real roots. In which case then you can substitute in the M1 and M2 values. All right, so what happened? How did M1 and M2 happen? Well, this one up here, this M we're solving for here. But remember, you'll have the plus and you'll have the minus root, right? So in fact, you'll get out 2 M's. So substitute in the M1 and M2 roots values, and they will go into this equation. Y of x equals. Remember we were saying we're going to be trying to guess a y. Well, here is the form of the y. It is the solution to this problem. C1 e, this is natural e, to the power of m1 x plus c2. C's are the constants, c2 e to the m2x. Let's just take a look at what we've got here. So remember we said to solve the differential equation, we're trying to guess some y, which is the quote variable of the original equation. So here is our functional form for this. This is the answer if you have 2 distinct real roots, but you can plug in the information that you got. You can't just copy and paste this equation as written. You need to then substitute in your m's for a particular problem, which will work out momentarily. So we've got 2 m's, remember, because we have a plus and a minus root. So you'll have one of the m's goes here and the other one goes here. But what do I do? How do I know which one is m1 and which one is m2? Well, in fact, it doesn't really matter, right? There are 2 constants and there are 2 m's. That's really all that matters here. Okay, and this is a function of x, and so here are x variables, which are showing up here. And so yeah, that's the form. It's of the form e to the x. We have m1x, so m1 then becomes your constant, and your c1 and c2 are your integration constants, which we do not know, but we would be able to figure out if we knew the boundary conditions, which we will be investigating later today. All right, case 2. So you could have 2 of the same, 2 equal real roots. So in fact, what that means is just m1 equals m2 when you solved above. And so then you just get basically the same thing. So case 1 and case 2 are really sort of the same thing. Y of x equals c1e to the mx plus c2 e to the mx. So basically the only change is that instead of having m1 and m2, you just have the same m in both because they came from the different roots. Okay, easy. Case 3 is more complicated. That's when you have your imaginaries coming into play. So case 3 is the one you don't want to see. Complex roots. But we can learn how to handle this. All right. From inspection of the complex solutions, you're going to need to deduce the real part and the imaginary part's coefficients. Deduce A1, the real part, and B1, the coefficient of the imaginary part. And sub into the equation. Repeat for A2 and B2. All right, so remember a few things we need to remember. So our solution is going to come out in the form M1 equals A plus BI, A plus BI, and M2 equals A minus BI. And this again came from that quadratic equation right here. So you're going to have a plus and a minus root, and you're going to recognize it because the thing inside of this discriminant is going to be negative. Okay, that's how you're going to know that we're now in this situation. So here's your generic solution of A plus BI and A minus BI. Really all we need to know is this thing, the A and the B, which is what we're saying here. We need to figure out what that is. And that you substitute into this form, y of x equals e to the ax times C1 cosine bx plus C2 sine bx. Oh, it's waves. Sine and cosine. Yes, it is. All right, so the next things. All right, so basically that's what gives you the answer. Okay, so those are your 3 cases, and at that point, you have the solution. Okay, so let's just mark that. At this point, we have the solution for an equation y of x, right? This is an answer to the second order linear homogeneous, second order linear homogeneous Diffie cube. Done, right? Well, depends. Some of the other things we can do is we could solve for C1 and C2 if boundary conditions are given. You've probably done this sort of thing in kinematics in your intro physics class in high school or even in college. And so this is how you would do that. All right. So at this point, though, let's just lay out what we're going to do for the rest of today. There's a couple of things we need to do. What we need to do is we need to actually work this out with some equation that's got numbers in it, because this may all be feeling a little bit abstract at the moment. So we're going to do it again, but we're going to do it for a specific equation. Then what we're going to do is we're going to try to solve it with the boundary conditions. And then remember that we're going to have the situation where we might have the different kinds of roots. So our first example is we'll keep it simple and we'll solve where we have some real roots. But then we would also do an example where we are going to have the imaginaries. All right, so let's do an example. So today's example 1. Example 1. Sometimes this pen doesn't write on certain places. I'm not sure why. All right, example 1. Here's the problem. Solve. This is the instruction. Solve the equation. And that's the instruction you get. And it's going to look something like this. D squared y over dx squared minus 3 dy dx plus 2y equals 0. All right, so does this meet the criteria? Is it written in the descending order for the derivatives? Second order derivative, first order derivative, 0th order derivative? Yes. Is it linear? Well, we'll find out when we get y. Homogeneous, that means it should be set equal to 0. Already true if we had if the minus 2y were on the other side of the equation, we'd need to move it over. The other thing we need to check is the leading coefficient. What is the leading coefficient? It's supposed to be set to 1, and is it? Well, I don't see any leading coefficient, no number written here, so that's terrific. The leading coefficient is 1. Great. Next thing we need to do is we need to find our P and Q by inspection. So I'm actually going to just switch over to the Newton notation just to make this easier. Y double prime. So I'm going to even write this out explicitly. 1y double prime minus 3y prime plus 2y equals 0. All right. So remember that we're trying to match this up to the equation y double prime plus py prime plus qy equals 0, and we need to deduce p and q. So this is, by the way, this is step 1. ID P and Q. All right, that's what we're working on here. All right, so we take a look at this and we see that by inspection, P equals -3 and Q equals 2. Great, step 1 is done. Next, step 2. We need to substitute into the auxiliary equation. The auxiliary equation. So how do you do it? All right, so we'll be doing some substitution. So we have m squared plus pm plus q equals 0. This is the given auxiliary equation. Great. Now we're going to substitute in. So we have m squared plus what's p? It's -3. And when I substitute things in, I put them in parentheses. That's just to show that it's substituted in. And sometimes if you have something more complicated, it's useful to keep that separated out. So you'll just see that's the way that I do math. Okay, plus q, which is 2 equals 0. So this is just sub in P and Q. All right. Next thing we're gonna do is now we're going to solve using the quadratic formula. Okay, so now we're going to do m equals -p plus or minus square root, right? This is p squared minus 4q to be derived above all over 2, right? This is the from the quadratic formula. And then we just substitute in, all right? So now we get m equals negative p, right? Negative of -3 is going to be positive 3 plus or minus the square root of p squared. That's going to be 3 squared, right? Minus, well, -3 squared minus 4 times q, which is 2, all over 2 times a, which is 1, right, in this case. And so then we can, okay, so here we just subbed in. And now we're going to go ahead and simplify. So in other words, m equals 3 plus or minus, what's -3 squared? That's 9, minus 4 times 2 is 8, all over 2. So this is equal to 3 plus or minus the square root of 1 over 2. What's the square root of 1? Square root of 1 is 1, so it's 3 plus or minus 1 over 2. All right, so this is all just simplifying. All right, and so now we're going to have our plus root, and then we're going to have our minus root. So in other words, m1 equals, this is our plus root. I'll just put a little plus up there. 3 plus 1 is 4 over 2 equals 2. And our m2 equals, and this is the minus root, 3 minus 1, which is 2 over 2, which is equal to 1. So here we have our solutions. These are our m values right here. m1 equals 2, m2 equals 1. That's the answer for our m's. So in other words, we have 2 real roots. Great. Step 3. Select the correct solution and sub in. Make the solution form and sub in. All right, so for 2 real roots, this is case 1, 2 real roots. Great. So it's gonna be like this. So we're gonna do y of x. So we just simply look it up from above, equals c1 e to the m1x plus c2 m2 x. Oh, e to the yeah, okay. And then all we need to, so this is the given solution for 2 real roots. From math. Okay, now we're gonna sub in m1 and m2. All right, so how do we do this? All right, I'll copy it over. And you see that I'm doing this in the proof style. Now, this course isn't a math class, but there's certainly a lot of things we can learn from our math friends, and it is a good idea to be rigorous about how you write your things. So I like to write it on the left and I put the reason on the right. And then when I'm going back and reviewing it, I know why I did what I did. C1E, what's M1? M1 is the plus root, so that's 2. Again, I will do this parentheses to show I substituted something in, and then I can always remove the parentheses if I don't need it in the next round. C2 e to the, what is M2? It's 1 x. So of course, 1 times x is not needed, and these parentheses are not needed. So now I can just go ahead and clean that up after I've taken the time to write that in. C1e to the 2x. Well, this looks terrible. I have lotion on my hands, so I think it's sometimes messing up the screen here a little. Okay, C1. It's very dry weather. Let me just polish this a little bit and see if that helps. C1e to the 2x plus C2e to the x. Ta-da! And let's just double check. Yes, that's what I got. We got this before. All right. Suppose we want to verify the solution. Okay, so here's the answer. Okay. Verify the solution. How does that work? Well, this constitutes is going back and showing that it worked. Okay, so you'll go back to your given differential equation. D squared y dx squared, given in the original problem, minus 3 dy dx plus 2y equals 0. This is given differential equation. Now, do you agree that if we've gotten the y correct, that we should be able to take these derivatives and use these numbers here, and it should equal 0? That's how you would check it, and that's exactly what we're going to do. So what we're going to do is we're going to solve for the required derivatives. All right, so which derivatives do we need? Well, we need the first and the second derivative. So here we have y of x equals c1e to the 2x plus c2e to the x. That was our solution from above. All right, now we're gonna need to take our derivatives. So now I'm gonna use a Newton notation, y prime of x equals. Well, how do you take the derivative of this thing? Remember that the derivative of e to the ax. So d dx e to the ax equals ae to the ax. You remember this one? All right. So what we're gonna do is, so you see this is the a. Okay, this is a different a than the a we talked about before, right? This is just means it's a constant. Okay, so what's the derivative of c1e to the 2x? It's gonna be wait a sec. I wrote that I did this backwards from how I did it before. Actually, it's fine. It's the same thing. Okay, so what we're going to do is we're going to have 2 times C1, 2C1, and I told you I was going to put these in parentheses. All right, let me just be a little more consistent here. So 2 is the coefficient. That's 2 times C1e to the 2x plus. Now, what's the coefficient here? Well, the coefficient is 1. C2e to the x. All right, so now we have, that's our first derivative, 2c1e to the 2x plus c2e to the x. All right, good. It's the first derivative. Now we also need the second derivative. Second order differential equation, you need 2 derivatives. So we're going to do y double prime equals, now we're going to do the same thing again. So it's going to be 2 times 2c1c to the 2x plus, and our coefficient again is 1 up here. So it's going to be 1 times c2e to the x. So then we can simplify that. So this is taking the first derivative, the second derivative, simplify, and here we have 4 4c1 e to the 2x plus c 2e to the x. Okay, and that's the simplify. Great. Now, substitute the derivatives back to the original equation. Right, so it says, where's the original equation? It's right there. Okay, now we've mixed the notations again. So this one is d squared y over dx squared is the same as that, and dy over dx is the same as y prime. Okay, and this is y. Right. All right, so that's Newton's versus Leibniz again. All right, controversy. They were fighting in real life, and there's controversy continues to this day as we are writing our calculus. All righty, so now next thing we're gonna do is we're gonna substitute these things in. So we're gonna say, all right, d squared y over dx squared, second derivative. What's that? So I'm gonna use this square brackets because we have whole formulas we need to put in. So we got 4c1 e to the 2x plus c2 e to the x. Okay, that's the whole formula. Plus, now the next thing we need to substitute in is, oh, it's not plus, it's minus. All right, I'm gonna fix that. Do a minus. All right, minus 3 times this thing, dy dx. Well, what's that? That's the y prime, which is 2c1 e to the 2x plus c2 e to the x. Great. And now it's plus 2 times y, plus 2 times, well, what was y? Y is this thing. C1, no, 2. Let's clean this up a little, sorry. Having good handwriting is not my forte, and it really helps keep things organized. Plus 2, that's this 2, times, what's y? Y is c1 e to the 2x plus c2 e to the x. All right, there we go. Equals 0. All right, so now what we're going to need to do is we're going to need to distribute these all out and then match up the similar terms and go ahead and combine these out, and we're gonna really hope that all this cancels out. Let's see what's gonna happen. All right, so this first one has nothing special going on, nothing to distribute, so I'm just gonna bring this down. 4c1 e to the 2x plus c2 e to the x, and it's not in parentheses anymore because it's all distributed out. Now I'm going to distribute the minus 3 over these, so this is going to be minus 3 c1 e, no, 3 times 2 is 6. That's 6 c1 e to the 2x, and minus 3 times this will be minus 3 c2 e to the x. All right, now we got this plus 2 over here, so we're gonna have plus 2c1 e to the 2x plus 2 times c2 e to the x equals 0. Now, and let's put a question mark above this because we're currently verifying it. All right, now what we're gonna do is we're gonna put together the ones that have the C1s. So this might be a helpful thing to do. I'm just gonna grab my highlighter here. So my C1e to the 2x's are gonna be this term, C1e to the 2x, that's this term, and c1e to the 2x, that's this term, and the other terms are gonna be these ones, right? This is e to the x, Good. All right. Now we've matched them up. That you don't have to do that, but I just find that helpful to keep things sorted. So we got 4c1 e to the 2x. So I'm just gonna regroup them, right? Minus 6c1 e to the 2x plus 2c1 e to the 2x. Those are all the blues. All right, plus. All right, and so we can already see, this is looking good because those cancel out. 4 plus 2 is 6 and minus 6 and the base of the term is the same. That cancels out. Let's hope that this also works for the pinks. So we got c2e to the x from here, minus 3c2e to the x, good. Plus 2 c2e to the x equals question mark 0. Does it equal? All right. So we're gonna just now go back over to here. Alrighty. So these are our the pink ones. And we also have our blue ones over here. Let's see. And now, does it work out? Equals. Okay, 4. Okay, so we already verified this one goes to 0. You can verify that for yourself. If you don't trust, you don't see that. Okay, so now we got minus 3 and a plus 2 and a plus 1, which is plus 3, and that's a minus 3, and these are all e to the x terms. Ha! 0 plus 0 equals 0. Verified. All right. Yes, it works. So we can now write a QED. But Aaron demonstrator. So this means that that was in fact the solution because it holds true. All right, so to just zoom out for a second here and recap on this, what we wanted to look at is we did an example of solving the equation, right? So we talked about the generalized way of solving this thing. Now we've solved the equation for a specific equation. We made sure that it is in fact meeting the criterion for a second order linear homogeneous differential equation, which it does. We checked for the leading coefficient being 1, which it is. We made sure that it's in the descending order, which it is. And then we solve for P and Q, which are -3 and +2 by inspection. Then we went into the substitution into the auxiliary equation, which substitutes in those P and Q values in order to get out the answer. And we got the answers out that are M equals 2 and M equals 1. Those are our two solutions, which are two real roots. So we can then take those and take the form for the two real roots, which we just look it up, and we substitute in and we get out our wave equation. But we'd always like to verify that that's correct, right? Is it really true? And so what you can do to verify the solution is you substitute back into the original. So you have a y, right? That's what we solve for. And the question is, does that y in fact satisfy the conditions that we were looking for? Because we were trying to guess a y and now we've guessed one. So it should be fine, but why wonder when you could actually check it? So we went ahead and we actually verified about whether or not this was a solution. So in order to do that, we're going to need to get a couple of derivatives. So we calculated up the derivatives that we need. That is so we had our y from solving the auxiliary equation. We took the first and the second derivatives, and then we substituted those back into the original equation using those coefficients that are provided. And in doing so, we were able to demonstrate that, in fact, both of these solutions, the solution added up to 0, which means that it satisfied the equation and therefore it is correct. All right. Next thing we could do is boundary conditions. So what we recognize is this is the general solution. And how do we know that it's the general solution? Well, the reason why it's the general solution is because notice that the C's still don't actually have any numbers. So the next thing we could do is we could solve with boundary conditions. With boundary conditions. Note that if no boundary conditions are given, then you're done. Okay, but if you do have boundary conditions, then we're going to need to solve it. So let's say, let's make up a problem. Let the boundary conditions for the above problem be given as y of 0 equals 0 and dy dx equals at x equals 0 equals 1. Let the boundary, whenever you see that word, that's going to be a key word that you need to do the next step. So this would obviously have to be given. Y of 0 equals 0. Dy dx. Okay. So the general solution has been solved above. So when you get a question, you always want to think about, do I need to go through all those steps to solve this? Right, so the problem may just give some boundary conditions in your differential equation and not tell you you need to solve it. But you need to be thinking, do I need to do all those steps to solve the differential equation first? Because you need to do that before you can apply the boundary conditions. All right, so here we go. So we got y of x equals c1 e to the x plus c2 e to the 2x. Okay. Notice that it has the c's, right? This part right here is what's telling us boundary conditions are not solved. Right, so when you solve the boundary conditions, we will get the answer to those c's. That's the whole point of this. All right, so next what we can do is we'll now solve for the specific values of c. We can do this, yeah. I think I keep getting the lotion or moisturizer on the screen because it's very dry right now, which makes the pen not work totally great. All right, anyways, so yeah, that's what that was. I was attempting to wipe the screen, keep it clean. All right, so we now solve for the specific one. So consider condition 1. Condition 1. So what did condition 1 say? Y of 0 equals 0. This is a given in the problem above. So what do we do? Okay, now we also have our solution from above. Y of x equals c1 e to the x plus c2 e to the 2x. Right, this is a solution from above. All right, now what we're going to do is we're going to substitute in. So what does it say? It says y of 0. So in other words, when x equals 0, the answer is 0. So we're going to substitute that information in. Okay, so now what we do is we do y of 0 equals c1e, oh, we know what x is, substituting 0 plus c2e to the 2 times, oh, we know what x is, it's 0, equals 0. Okay, this is sub in x equals 0 and y of 0 equals 0, which was the condition, right? That's what the condition said. Now we're going to simplify. Equals, what's e to the okay, e, anything, really, anything, not even e to the 0, anything raised to the 0 power equals what? 1. So we're going to make use of this fact. So c1 e to the 0, oops, we can solve that. The whole point of this, e to the 0 is 1, right? C1 plus C2, what's, oh, 2 times 0 is 0, e to the 0 is 1 equals 0. So in other words, we have C1 plus C2 equals 0. Terrific. This is our first result. And the boundary conditions. Next, we consider condition 2. dy dx for x equals 0 is -1. This is again given. So, in other words, y prime of 0 equals 1. Let's just mathematize it. Okay, next what we need to do is now we need, well, what is y prime? Well, we already solved that, it's up above. Okay, y prime of x. You see how Newton's notation is quite helpful for this, so we're not spending all the time writing all our derivatives. C1e to the x plus 2c2 e to the 2x. All right, great. Now we sub in. Okay, this is from above. Remember, we wrote out our little table and we already solved for that. Great. So now we said y prime of 0 equals 1. So now we got to put in all the x's at 0. C1 e to the 0 plus 2c2 e to the 2 times 0 equals 1. Oh, -1. Sorry, negative. Those are negatives. -1. All right, great. Now we got again equals C1. We got the same trick plus 2C2 equals -1. All right, terrific. We have another. One. We got two solutions. Two variables. So we now solve the system of equations. From algebra. All right, so we got C1 plus C2 equals 0, and we got C1 plus 2C2 equals -1, right? This is the system. And so, okay, right, the system of equations. Next, what we're going to do is we can multiply the bottom by -1. All right, so let's do it again. C1 plus C2 equals 0, and we're going to multiply through by a -1, so I'm going to put a -1 out here. So we're going to have negative C1 minus 2C2 equals 0. This is our revised system, and it's an allowable operation. And now we're going to add them together. That's an allowable operation. So these cancel. So, and C2 minus 2C2 would be, so it would be 0 minus C2 equals, wait, this is wrong. Sorry, -1 times 1, this turns it into a +1. Sorry, equals 1. That's correct. And then we move the minus sign over and we get C2 equals -1. All right, we have an answer. Okay, add. All right, now we can substitute back in. Then we go back to the first equation. C1 plus C2 equals 0. Now substitute in. Okay. select one from the system. Now you substitute in that one. So C1 plus, what's the value of C2? Minus 1 equals 0. And that gives us C1 equals 1. All right. So this is just from the system. C2, and then so simplify. All right. So here we have now our constants. So what this means is we can now go back to the general form and we can actually fill it out. So we started with the equation, and now we can go ahead and actually finish that. So let's write the final answer to the diffie-qs. Y of x equals C1 e to the x plus C2 e to the 2x. This is the general solution. Then we got this from solving the diffie-q, right? The auxiliary equation and so on. Now the next one, y of x equals, now substitute in your c values. What's C1? 1 e to the x plus, what's C2? Minus 1 e to the 2x. This is sub in the constants. Which we got up here. All right. C1 equals 1 and C2 equals -1, which were the boundary condition solutions. And now we do this. Y of x, I'm just going to simplify that, equals e to the x minus e to the 2x. This is the solution to diffie-q, subject to boundary conditions. That's what we've just solved here. All right, now, what we would also like to do is we'd also like to see how this solution would work out using the complex roots. Right. So in fact, actually the procedure is pretty similar. Hopefully you're starting to see the pattern here that the things are repeating. It does take a bit of practice before you see that, so I do encourage you to review at home if you're still feeling a little fuzzy about this. So it's very similar kind of thing. All right, so how do I know? Because I already solved it before I wrote it down. That's how I know. Because when you get a question, you're not going to really know. Okay, so the directions are going to say solve, right? Not something like that. Okay, d squared y over dx squared. So we have a new problem now. Plus 0 dy dx. Now this term may not always be given as a 0. It's 1y equals 0. I'm going to write it all out for you. Y double prime. So I'm going to write it with Newton's notation. 0y prime plus 1y 0. Right, so that's Leibniz. Okay, this is given Newton notation. All right. So so this is step 1. ID, P, and Q. All right, so by inspection, I can see that P equals 0 and Q equals 1. All right, great. We're already on to step 2. Step 2. sub into the auxiliary equation. And solve it. So we got m squared plus pm plus q equals 0. Sub in your values. This is auxiliary given. And now we're going to sub in the p and q values. M squared plus, what's p? 0. M plus, what's q? 1 equals 0. Sub p equals 0, q equals 1 from above. From step 1. Great. Next, we're going to put this into the auxiliary equation. M equals negative b squared negative b plus or minus square root b squared 0 squared minus we have a 0 minus 4 1 times 1. The discriminant is gonna be negative. This is how we recognize that there is a problem. All right, so what about that? All right, sub into equation. Right. Discriminant is negative. All right, we need to make sure of that. Okay, so let's go ahead and clean this up. M equals plus or minus square root of negative 4 over 2. What's the square root of minus 4 equals plus or minus 2i over 2. We can pull out the 2 equals plus or minus I is our roots. So the positive root, so we're going to have this. M1 equals 0 plus 1i, right? So I'm writing this explicitly out in the full form. A plus bi. A, right? So this is a plus bi. Okay, this is just simplifying. This is write out the roots. Okay, so a equals 0 and b equals 1. Remember, we're going to need this info for the next step. This is the plus root, and then from here, this goes plus, and then we also have the minus root. So let's do m2 equals 0 minus 1i. So we have a plus bi. So a equals 0 and b equals negative 1. So this is our info from the second negative root info. Step 3, sub into your form. So we've identified this is complex. Sub to appropriate. So again, we tap the shoulder of our math friends. We can go back to our info from above and we see what the functional form is. So again, we have a equals 0 and b equals 1 for our positive root. Then we do this, we have y of x equals e to the ax. This is why we need the a's. C1 cosine bx plus C2 sine bx. X. All right. This is the general form for the complex roots. And next what we do is go ahead and sub in e to the what's a is 0, up 0x. Sorry, that keeps going weird. C1 cosine b, what is, oh, yep, we know what b is. We know what b is, cosine 1x plus c2 sine, we know what b is, it's 1x sub in b. And now this is equal to anything to the 0 power is 1. So we're going to have c1 cosine x plus c2 sine of x. Let's just simplify. Okay, now let's just note that you could, oops, you could also do the same for the minus root, and you could also verify these solutions by substituting those back in the original equations. Alrighty, so then, sorry, I apologize. We are maybe a minute or so late here, but this is a big topic. All right, thanks to you all for joining us today. What we have talked about today is the procedure for solving linear homogeneous second order differential equations. That was a little out of order. It's a lot of stuff there. So hopefully this has been really helpful, and seeing how you would actually push the numbers through and actually solve one of these things. I've given you both the general form and also taken you through a couple of examples here on how to actually do this. Now, we did leave a little bit of work for you to do on your own. In this last one, working with the imaginary roots, but really the procedure is just exactly the same as we have done, and we'll have opportunity to see more of these when we work our problem sets. So hopefully this gives you an idea of how you can solve these things and makes it a little bit more tangible. Now, it's really important, I'm just going to say this again, it's really important that you make sure you know how to do this, because it's going to come up over and over again as we are solving things in the quantum mechanics section of the course. So you want to make sure you're really solid on what the procedure is, and then also that you just have some working facility with actually plugging some of the numbers in these and making sure you can push those through. So again, our general procedure is you have the differential equation. We've talked about how you can identify it as being second order, how to identify it as being homogeneous, and then making sure you put that into the correct rank order with the highest power first. So the first power should be second derivative, right? Second derivative, first derivative, plane equation equals 0, right? Then you go ahead and you solve that thing using the procedure we outlined. So it basically becomes like solving a quadratic equation. So you identify your P and Q, make sure your leading coefficient is 1. If it's not, you just divide out by it, identify your P and Q, and then go ahead and substitute those into the auxiliary equation, which is basically just the quadratic formula that you learned in high school. You can solve it by factoring, you can solve it by using the quadratic formula. That will always work. So I would just do that. And then you get out your answer. Now, at that point, you have your generalized y equation, which still has the c's, the integration constants, not known, right? So, but you do know the generalized solution at that point. So then what you can do is, if there are no boundary conditions, you're done, declare it a day, you're finished. But if you do have boundary conditions, you need to then apply those boundary conditions to what you have. So you need to read what it says for the boundaries, and then you need to apply those boundaries to actually solve the equation. So typically you'll see what we saw today, is you get a system of equations, and then you would solve for each of your integration constants C. And once you have your integration constant C, you can take those and you can substitute them back in. Now, at the point that you have just your generalized solution, you can go ahead and go back and you can take the derivatives. You'll need the first and second derivative, and then you can substitute those back into the original equation to demonstrate that you in fact do have a solution to your differential equation. As we'll see as we move forward, it's possible that you could get more than one solution. So in today's, it's been a little bit simpler, but we're going to then move ahead to try to see some other situations. All right, so hopefully that gives you some good sense of what's going on here. As I mentioned at the outset, there is a handout that goes along with this, which will be on the class Moodle page. We can make that available to people. It basically outlines just what we talked about for those different steps of solving with the auxiliary equation, and kind of gives an idea of like substituting in different equations for the different models as we're solving those other quantum mechanics problems, because this basic outline is what will happen over and over again. All right, well, thanks so much for joining us. Looking ahead to the next time, we're going to look at solving the classical wave equation. And then after we have mastered that one, we will go ahead and move on to solving some of the more quantum mechanical ones. Classical wave equation requires separation of variables, so we will start off with that next time. A little bit more math, but hopefully we'll be getting into some of the actual applications really soon. Thanks so much, everybody. Hope you have a great day. We are, like I said, almost New Year, so happy New Year 2025 if you're watching this now, and if you're in the future, I hope that your 2025 and years beyond are going great. Bye-bye.